Today.
Okay, thank you very much. What I plan to do today is to spend roughly half of the time talking about classical glasses, but very, very superficially. I won't give you much details, but at least explain to you what's the problem and why it's difficult to solve. And I will extract from what we know about the behavior of classical glasses one quantity, one observable, that plays the role of an effective temperature for these systems which are out of equilibrium, and that has been measured in many different situations, and I will explain you a little bit which cases are understood, some of them analytically and some of them just numerically or experimentally. And then I will go into the quantum field to tell you how this idea carries through and goes into the quantum situations as well. And then the last part of my talk will be about relations between this effective temperature that appears in the context of glassy systems and the ones that appear in the context of generalized Gibbs ensembles in the dynamics of closed systems having quenched in some way, evolving out of equilibrium because of some changes in their parameters. So actually, this paper that includes the results that I will explain at the end of the talk, is a result of discussions last year with Robert Koenig, who was here participating in the parallel workshop in which I was. And out of discussions that followed a seminar that I gave, we wrote this paper, and that will be the main content of my talk today, or the main part, new part, let's say, in my talk today. So I wrote here below the expression of the fluctuation dissipation theorem in the quantum version of it for bosonic operators. I will use it later. This is why I want to keep it here just to remind you what's the expression. So this is correlation functions, these are response functions, but I will define this later in my talk. So let me start by talking a little bit about classical glasses. So classical glasses are just an ensemble of particles that interact in some way. There's no quantum mechanics for the moment in my problem, so I have a box, let's say, and I have particles in that box. Let's say that the box has volume, number of particles n, and I couple this system to a bath. So if this is the system I will be interested on, I will couple it to a bath. So if I want to describe this problem with a Hamiltonian, I will have the part that corresponds to the system, the part that corresponds to the bath, the part that corresponds to the system bath coupling. And I'm using the same language that was used yesterday or the day before in a talk here. So the bath is supposed to be in equilibrium. At some temperature T, and this is the temperature that I will include here as control parameters for the behavior of my system. So if I want to follow the dynamics of this problem, I will write down dynamical equations for the evolution of the positions and velocities of my particles, and these will be from here, just Newton equation. And because of the coupling to the bath, I will have Langevin terms that will imply dissipation and fluctuations induced by this coupling to the bath. Okay? Now, the problem is, imagine that you take the configuration of your system to be in equilibrium with the bath at some very high temperature. So you put this temperature of the bath to be very, very high. Again, exists upon the fact that this is the temperature of the bath to be very high. So under those conditions, my system will be in contact with the bath and will be in equilibrium typically with the bath, because the dynamics imposed by the bath will be very fast on the system, and it will be able to exchange and communicate with the bath efficiently and then equilibrate with the bath. So initially the system will be typically in some liquid configuration in equilibrium with the bath. And then what the experimentalists do is to change the temperature of the bath with some protocol. Can be slow, can be fast, different choices. And see what happens with the dynamics of the system in contact with this new bath, which is characterized by some new temperature. And what's observed is that when this temperature of the bath goes below some characteristic value that depends on the system in question, the system will no longer be able to equilibrate with the bath. It will fall out of equilibrium, and it will evolve in a way that is not the one characteristic of a liquid, it's something else. So it will fall. Equilibrium for temperatures below some G, which is not very precisely defined. It's more like a dynamic crossover than a natural phase transition. But definitely the dynamics of the system changes when the temperature of the bath goes below this value Tg.
It could be a crystal, I guess, too.
It could be a crystal, but what happens is that for certain potential interactions between the particles, the system jumps over, if you will, just ignores the crystallization transition towards the crystal. It continues going down following the temperature with some configuration, which is typically called a supercooled liquid. And then below this Tg, what happens is that it falls out of equilibrium. So how do we see that, and how do we experimentalists see that? One way, which is the typical one that you can see in all the reviews that deal with glassy systems, is to work under conditions in which the volume is not fixed, but it's the pressure which is fixed. And then the volume of the sample is controlled as a function of temperature. And what you see is that at very high temperatures, something like linear relation, and then the crystallization or melting transition, let me call it Tx, would be there. But under cooling, the system just goes down and ignores this. So this would be the liquid. This is what is called the supercooled liquid. And then below this Tx at some value Tg, you will see a change in the behavior of this curve. And if you do the cooling at different speeds, what you will see is that there is no sharp value of this Tg, that it displaces a little bit with the cooling rate that you use. So these curves correspond to different cooling rates. And the fact that below this Tg you don't have a unique value of the volume associated with temperature means that the system is out of equilibrium. There's no unique relation between the observable and the control parameter. And, well, you see different values depending on the way in which you prepare your sample. So there are other kinds of measurements, of course, that can be done. And this, as I was telling you, is also observed, for example, in numerical simulations when you choose for the interactions, let me call it with a V like this, between the particles. For example, a Lennard-Jones kind of potential, so potential that depends on the distance between the particles, and that has some kind of form like this, with a repulsive and attractive pieces that involve some kind of frustration among the positions that the particles would like to occupy in the sample, and for sufficiently high density, you will see this kind of behavior like that. So the message here is that there is some value Tg where the system behaves, below which the system behaves out of equilibrium. Now, the times over which you will see behavior like that are extremely long. And there is no way in the lab or in your numerical simulation to do this procedure sufficiently slowly to reach equilibrium below this TG. Okay, so it's out of equilibrium, but it's out of equilibrium for all times that you can reach experimentally or numerically. So what this means is that the equilibration time below this TG is much longer than the times that you can reach in your lab. Okay. Now, this is not the fact that a system which is made of many particles or many agents in interaction falls out of equilibrium at a given temperature under these quenching procedures is not unique to glassy systems. There are other systems that we understand better that also do this kind of similar kind of falling out of equilibrium phenomenon. Those are the systems that, for example, just to give you a very simple case, phase separate. Okay, so if you have, imagine a mixture of two kinds of particles or atoms, A and B, and you include interactions such that A wants to be next to A, V also wants to be next to B, but A wants to be far away from B. Okay, so they want to phase separate. But if you start from an initial configuration where these are mixed, typically of very high temperatures, and then you quench below some critical temperature, that will depend also on the density of the two species, but imagine that you have a 50-50 mixture, to make it simple. And then you quench it below some temperature. These will try to phase separate. They will try to, be in regions such that these are reaching A, let's say, and the other ones are reaching B, let's say. But this phase separation, this corseting or domain growth processes, takes time. This problem can be understood. It can be visually understood because you see the phase separation of the two species. It can be also analytically understood or described. And what you find in this problem is that the typical length that we call psi d of time, the typical size of these domains with order grows like t to the 1/3. And if you estimate an equilibration time for phase separation by requiring that this growing length be of the order of the system size, so the linear size of the box, then from here you just obtain that this TL goes like L cubed. So it diverges with the system size. So for infinitely sizes for the box, this time diverges. So this is an example which is understood, phenomenologically and also described in different ways with analytical methods, but where you also have a diverging timescale below some critical temperature. The problem with the glassy systems is that we don't have any visual understanding of whether there is some growing length, whether there is some kind of order controlling what's going on below this TG or not. So we don't have this feeling or this understanding. Okay, so this is why this problem is difficult. We don't see visually any difference in the structure between what happens below TG and what happens above TG here. The figures, the configurations look pretty much the same. They look pretty much the same, but they don't behave in the same way. And they don't behave in time in the same way. Because if I do measurements of correlation functions here, I will see stationary behavior. That will precise what I mean by this now. While if I do the measurements here, I won't. So here I will see that there are non-trivial waiting or time dependencies that are not present on this side of this TG. So it's really the dynamics that's telling me that something different is happening on these sides, two sides of Tg, while from the structure I don't see much. So how can I quantify what I'm saying? By measurements of correlation functions and linear response functions, for example. So in the case of the particle system, what people typically measure is a density-density correlation function. So I will write it like this. So this expression that I wrote here is what people call incoherent scattering function. It's just the contribution from different particles to the density-density correlation function. This is the wave vector. And this is the position of particle I at, I forgot to write the time dependencies, time t minus the position of particle j at time tw. So I'm defining times. Let me write it here. This is the moment of the quench, say the moment when I went through, when I reached the temperature at which I want to work. Imagine that I have now a procedure in which I do infinitely fast quenches to simplify. So this is the moment where I reach the temperature of the bath at which I want to measure. And then I call t waiting and t two later times. And this is the density-density correlation function at these two times, and this is the wave vector at which I want to measure. So this is a correlation function. I can also observe or compute a linear response function, which, well, there's averages, of course. So these are averages over initial conditions, or if you do simulations, random numbers in the noise. So it's a statistical ensemble average. And now I can do a linear response measurement. So I can perturb my sample with a kick in applying some perturbation at this time, waiting time here, TW, and see how the behavior of the observable I want to control or measure responds later after this T wait. Okay, so this is the linear response, and I'm going to write it in this way. Okay, H is the strength of the perturbation, and I'm looking at the response of this same observable that I was correlating up there. Okay, so these are pairs of linear response and correlation associated with the same observables. I could have chosen other observables, but let's look at this. So, if the quench is done to a temperature of the bath, which is in this region over here, these two observables are stationary, meaning that they are functions, different functions, but functions of t minus tw, so the difference between these two times. Instead, if the quench is done below this Tg here, then they are not. So they are not stationary, meaning that you cannot write them as a function of the difference between the two times. They are functions of the two times separately. So there is a memory in these correlation functions of the moment at which you either took the first image of your sample and then computed the correlation, or perturbed the sample and then computed the linear response. So there is a memory of this instant here, and this is an effect in the literature is called aging, but it's just a breaking the fact that the correlations are non-stable. Okay, so this is the first, it's another evidence for the fact that the system is evolving out of equilibrium. But then there is this other property of equilibrium dynamics that I want to discuss in the talk, which is the fact that for a system in equilibrium, these two quantities are not independent. They are linked by the fluctuation dissipation theorem in equilibrium. And what this fluctuation dissipation theorem states is, if I write it in Fourier transform, it states the classical limit of this expression that I wrote here. So the classical limit is just, taking h bar to 0, so omega, C of omega over 2 temperature. So in equilibrium, I can't do the Fourier transform easily with respect to the time difference because these two quantities are stationary, but out of equilibrium, I cannot, okay, in general. So there would be a waiting time dependence to be taken care of here and there, but just this is the result in equilibrium. And so another way to see that the system is out of equilibrium when you do the quantities below Tg is to compare this quantity to that quantity and see whether they satisfy some extension of this FDT that may take care of the waiting or not. So I insist, there is violation of stationarity and there will be also violation of FDT. So what do I mean by that? What I mean is that I can always take these two quantities here, fix T waiting, look at them as functions of T minus T waiting, comma T waiting. So I could do something like this. So I can fix the number T waiting here and do the Fourier transform with respect to the difference of the two times involved. In that way, I can compute C tilde of omega T waiting. I can compute R tilde, or the imaginary part of R tilde of omega T waiting. And I can compare these two for fixed T waiting and see what happens as a function of omega. The frequency. So what happens in these problems, in these glassy problems, is that although the FDT is also violated, it's violated in a way that admits the extension of temperature in this system, which is now out of equilibrium, to something that appears in the same position as temperature in the fluctuation dissipation theorem, but it's upgraded, if you wish, to an effective parameter. So FDT modified, where the temperature of the bath, which is what should have appeared in the FDT in equilibrium, is upgraded to some TF, a TF of omega TW, but with a very simple dependence on these omega and TW parameters that I can simplify, if you wish, in this plot here. I will plot TF as a function of omega times TW. And what will happen is that, let me write it as a function of 1 over omega times TW. What will happen is that this quantity will be something like this. with two plateau values, one at the temperature of the bath, and one at a higher value. So this one is higher than that. But there are two constants. Okay, so here it's constant, here it's constant, and there is a sharp crossover here. Between these two values. At a typical value, well, roughly of the order of 1 of this thing. So what's going on here is that although there is a violation of FDT, it's kind of simple. It's kind of simple because it makes appear the temperature of the environment like the system were in equilibrium. So here it's like equilibrium. And here it's out of equilibrium, but at a different value of the temperature. It's out of equilibrium. But at this time. So the fact that there are these two values can be argued and understood in the context of these systems here in different ways. I mean, I don't want to go much into the details of this because it would take a full seminar. But basically what can be argued is that when you have one of these glassy configurations, situations, where typically your particles are very packed because the density has to be high to have a glass in your system. What the particles are doing is that they are caged by their neighbors. So they cannot move very far away in short times because they are, packed. So in short times, what they can do, basically, and I mean, this is an approximation, but basically what they can do is they can vibrate surrounded by their neighbors. So whether their neighbors are ordered in a crystalline configurations or not, it doesn't matter so much. The fact is that each of them is vibrating quickly, surrounded by what's around it. This fast motion is the one which is controlled by the temperature of the bath, because the system doesn't really care whether it's ordered or disordered, or it has slow dynamics or doesn't have slow dynamics. This dynamics is fast. So this is the part which is here. It's high frequencies, so it's high frequency motion. So this is kind of vibrations within cages. If instead you go to the low frequency motion that corresponds to long delays between the two times, so long distances here that correspond to low frequencies, what you have to see is the actual structural relaxation of the sample, but this is very slow. And this is the one that knows that the system was not in equilibrium, was out of equilibrium. It's not a crystal, it's not a liquid. It's very slow, it's disordered, and so on and so forth. So the low frequency behavior of the system is definitely out of equilibrium. It's a structural relaxation, and it's the one that is controlled by this other value T star, which is higher than T bath. Why is it higher than T bath? Well, because you can argue, unwaveringly, that this long distance structure remembers the fact that you're coming from high temperatures. Remembers the fact that you have quenched from a liquid configuration to below Tg. So it has a memory of this high temperature initial state, and it has, for this reason, a higher value of T star. Apart from hand waving, this fact can be observed, can be better justified in certain models for which, for example, I can do the reverse quench. So analytically, for example, I can do the reverse quench in an XY model. You were asking me about the XY model. I can prepare the zero temperature state of the XY model and go towards higher temperatures and see the dynamics of the higher temperature at a higher temperature below TKT. And in that case, there's also violation of FDT, there is also out of equilibrium dynamics, but the T star that you will observe will be lower than the temperature at which you do the dynamics, because in that case you can quench from below to above. So from an ordered to a situation in which the system would like to be more disordered. Can also be done numerically, only numerically, in these interacting problems. In some lucky cases in which you can reach better equilibrium, you can be closer to equilibrium at lower temperatures and then heat the sample with numerics. And then observe this reverse of T star with respect to T bar. So, okay, there are many things that could be said about the values of this T star with respect to T bar, and justified also from a space point of view. But I will not, enter into these features now. Yes.
What happens if you try to create temperature gradient, right?
In the sample.
Pass heat current. So can you image, let's say, how it goes and which modes?
Yes, that's a good question. I don't think it has been done. No.
But in principle, in the simulation, so probably one could do it.
One could do it, exactly, yes. One could couple the bath to an external layer or put different temperatures up and down and see how it, yeah.
And so what is your intuition? So how would current go and how, sort of, which modes are responsible for it?
Well, everything that has to do with this T star are slow modes. Because the fast ones are the ones that communicate fast with the bath, and those will be controlled by the temperature of the bath.
Right.
So
you think it would be fast modes?
Yes, yes. No, it's slow modes. Slow modes will be controlled by the T star.
Mm-hmm.
While the fast ones will not.
Right, so slow modes remember where they came from.
Exactly.
And somehow there's decoupling.
Exactly. There is a decoupling. There is a decoupling, absolutely. This crossover that I'm showing here is a decoupling between fast modes and slow modes. Fast, degrees of freedom. The problem is that they're not really different degrees of freedom. They are the same degrees of freedom. So it's always the positions I'm talking about of the particles. But if I look at them at short time distances, they behave in some way. And if I look at them at long time distances, they behave differently. So
just want to know on which values does it depend? So you wrote omega and T. So omega means that for every mode there's a different temperature?
No, actually, okay, this is another thing that has been checked numerically and in certain models even analytically. The idea is that all the modes, all the observables that evolve in the same time scale, so in these problems, whatever the K I use, I will get the same value of T star.
So it does not depend?
It does not depend on the observable. But there should be some communication between them. They should be coupled somehow to as you were asking, exchange energy and, be in contact. If I take, for example, the positions and I compare them to the velocities, I could compute velocity-velocity correlation functions in these problems as well. The velocities are decoupled from the positions, basically, and they just couple to the bath. So those are fast. The velocities will not show any T star. Everything you will measure will be T bath, because it's a fast variable. And another way of thinking about it is that eventually this system would like to go to a Boltzmann distribution, right? Maxwell-Boltzmann distribution. So Maxwell-Boltzmann distribution is something like this for the velocities, and it's something like the potential for the, I have to sum over the particles, something like that for the positions, right? So these are decoupled. They don't look at them. They're different variables in my Hamiltonian way of thinking of this problem. So you see, this is just a Gaussian distribution, so it's trivial, the dependence on the velocities. While all the complexity is in the positions, where they are the interactions which are non-trivial, that don't allow the positions to equilibrate to this.
But so the beta here is now the effective temperature?
No. This is just the equilibrium, Gibbs-Boltzmann, or Maxwell-Gibbs-Boltzmann, VR distribution to which the system would like to equilibrate, although it doesn't. So the target distribution is this one. The velocities reach it quickly. The positions don't.
the omega are vibrational modes, no?
The omega is just the Fourier transform with respect to t minus tw. So it's a Fourier transform, and I go from t minus tw to omega. So what I'm claiming here is that if I do a correlation between times which are far apart, typically when I Fourier transform, what I'm looking at is low frequencies, right? And when I look at times which are nearby, I'm looking at high frequencies. Just.
I mean, so you're assuming the equilibration time is infinite, and
Yes.
that omega is going to 0 and TW is going to infinity, and
I'm
that's just a
assuming
function
that,
of the product.
yeah, but I can even do it for, in the simulations, of course, the W doesn't go to infinity.
But it has to be long to minimize.
It's long, yes. It's a long time limit, but can't be enormous. It's the times that people can do in simulations. You're not convinced?
No, so that's not dependent on omega or not?
No, but all this plateau here, it doesn't depend on omega. And here, it doesn't depend on omega either. But it's a cutoff where there is a cutoff, there is a crossover at when this variable is of the order of 1. I can show you more details on this if you wish later. But just remember that there is a quantity that comes from the FDT that admits the interpretation of a temperature. It can be measured with a thermometer. It can be checked to control heat flows. There are properties that you expect from a temperature that this quantity has. Now, let me go to the problem that it's the one that probably interests you more, which is the case where I will stick to classical problems in all my presentation and tell you how it changes when I do a quantum case later, because it's really the same for the two of them. Classical or quantum, it doesn't change much. So now what I do is I will consider a closed system, still classical, and I will do a quench by changing a parameter in the Hamiltonian and look at its evolution. So there is no longer a bath. There's just, okay, let me erase everything. And look at just the Hamiltonian of my system. And as an example, which encodes everything I want to tell you later on, I will take as a system a harmonic oscillator. Okay, so this is my Hamiltonian. Now, if the system is closed, energy is conserved, so the value of the energy evaluated at the initial conditions in note is a constant. Now, I can look at this problem. I can perturb this problem linearly, for example, to be able to compute a response function. And I can compute the correlation for the position of the oscillator, and this mean here means an average of the initial conditions, for example, if I have a distribution of them. And I can compute also a linear response function as before. In the limit of h going to 0. And this, of course, can be done analytically. It's very simple. So I will write down the results for this. Let me copy them, because otherwise I will miss some factors. So this is the linear response. Oh, sorry, I made. And the correlation looks like this. And what I've done here is that I have done an average over times, a window of times around TW to get rid of terms that are not stationary. There are some contributions that are functions of T plus TW, but I can kill those because they oscillate by averaging over a time window around TW. So these are the results. So now what I can do is I can Fourier transform, because it's easier to look at this problem in the Fourier transform version. I can Fourier transform these two. And let me write it here. So this is so the two expressions are equal to this. I'm just giving the values for omega larger than 0. There's another contribution from omega that's smaller than 0, but I'm not writing it. And this is the initial energy. That is the constant of motion, and then the other ones are the parameters. Now what I can do is I can do this ratio. I can do the ratio of that the FDT tells me to do, to see what I get for the factor that had to appear as a temperature. Okay, so I do this ratio here. And if I do that ratio, I will find that all the factors go, and I'm left with E naught. Minus 1, sorry. Minus 1. And notice that the frequencies will cancel because I have these delta functions here. So these relations hold only for one frequency, right? The frequency that is equal to the natural frequency of the oscillator. So this expression holds for omega equal omega naught. Otherwise, they are 0, the two forever. So, okay, this is just a trivial calculation. Now, let me see what the GGE construction for this problem would tell us to do. So, what's the GGE construction? So, the GGE construction proposes to find something like this, find the distribution function that a system that is not in equilibrium, but is isolated and is quenched in some way, will reach in its stationary state. And in particular, without entering into the details, for this problem, what the GGE would tell you to do is to identify the conserved quantity, which is energy in this case, and construct a rho GGE of V and X in the form 1 over Z E minus beta GGE, that for the moment you don't know what it is, times the conserved observable, which is the energy here. So the beta GGE you have to fix by requiring that the average over this distribution of energy, the conserved quantity, be equal to E naught, which is the value that is conserved. Okay, so I will write it like this. I won't use dV dx rho GGE dV x H system x should be equal to E naught. This is the condition that fixes beta GGE. So this calculation, of course, can be done. You just have to replace this exponential here, the expression of the energy which is there without the perturbation, that one over there, Gaussian integrals, you do this calculation, and what is found is that beta GGE is E naught minus 1. So now you look at this, and you look at that, and you notice, this is quite trivial, that beta effective, the one that I defined from the FDT, this here, yes, this side, of omega. So I will define it from the FDT by replacing temperature or inverse temperature by an effective parameter that may depend on frequency. Now you notice that beta effective of omega is equal to beta GGE. And actually, this beta effective of omega exists only for omega equals to omega naught, because there are these deltas here that select the frequency to be equal to the frequency of the oscillator. So what am I saying here? What I'm saying here is that you can obtain the Lagrange multiplier of the GGE distribution from the measurement of the FDT in the problem. Yes?
So it makes all happy and exciting and good, except one small caveat, which is that this ratio of things can exist even when omega is not equal to omega naught.
The ratio can exist? Well, it doesn't, no, because it's 0 and 0. Well, there is a 0 over 0, but
It depends on the order of limits, right?
Of course, it depends on the order of limits. But for omega equals to omega naught, this ratio gives you E naught minus 1. Okay, for this particular temperature. It depends on the order of limits, I agree. But let's say that at this selected frequency,
I mean, consider physically
yes.
a scenario where you
Yes.
start this closed system slightly connected to a bath. Okay, so it's a weak damping.
yeah,
And then these delta functions in frequency have some width.
yes,
By that damping.
yes.
So as I quench that damping parameter, presumably that leaves behind some imprint in this ratio, right?
Okay, but I don't want to look at the problem which is coupled to a bath. I want to look at the closed problem because
Well, it's
yeah.
the closed problem, but it's
Yeah.
how I got there, right?
Sorry.
It's how I quenched.
Okay, maybe
I don't mean to make a big deal about it. I'm
Yes.
just sort of curious, because I think you're going to get to a point where you have to look at other
sure.
frequencies eventually.
Yes, yes. So for the moment, I've taken this trivial example because it's just one oscillator where the calculations can be done trivially. What I want to insist upon the fact is that this is classical and has nothing to do with quantum mechanics for the moment, but the same calculation can be done quantum mechanically and I will find the same result, where instead of using this limit, I have to use that. Beta should be replaced by the beta effective of omega, and I can play exactly the same game, and I will recover the beta of the quantum GGE with the hats here and the hats over there, but it's not a quantum feature. It's a feature of the system being isolated. Then if you want to couple to a bath and take the limit, okay, maybe I could do the calculation. I haven't done it. I don't think it will change much, but yeah. You had a question? No, okay. No, I thought you were. Okay, so now what can I do to generalize this problem? Because you can tell me, okay, a single harmonic oscillator is trivial. I can repeat this calculation for many harmonic oscillators, so I can put sum over k here and put case and case and case, case and case, and the same will happen. So what will happen is that this will be generalized to having k here, having k there, and the omega selected will be the omega k, and the E naught here. So the relation will be replaced by the beta k of the GGE over there. So for each oscillator, I will play the same game with the selection of the frequency that I'm doing. Now, since you are more interested in quantum problems, let me tell you how it works quantum mechanically. This is just one one example of a quantum case that we have looked at to give you an idea of how it works. So the idea is the same. You just have to use the quantum FDT. So one problem we looked at is hardcore bosons. This problem that can be mapped onto fermions after Jordan-Wigner transformations. It looks like this. So this kind of problem with the Fs are fermion operators now. So this problem was studied at length in the literature. The conserved quantities are the fermion numbers. There it goes. So now, for example, which operator, which would be natural for this problem, can we use to compute correlation, to compute linear response, and to compare them, and to get the FDT and then the GG parameters from it? So in this case, for example, what one can check is that the density operator, I was calling it, so this is the density operator at wave vector q at time t. It emits an expression that looks like this. So this is a boson density operator, sorry. So it's a bosonic operator, this one here. So I can use the bosonic FDT for that one. And so if we do that, well, this is a kind of trivial calculation, but I want. Sorry. So this ratio will give you a tangent of lambda q being the lambda q's of the GGE, so the Lagrange multipliers of the GGE that we get from this FDT-like ratio here. And what are the omega k's? Well, the omega k's are selected in a way such that, now let me write it like that, omega q, omega q, to epsilon, 2, well, epsilon the energy. And the quench that I'm doing is going from delta different from 0 to delta equal to 0 at time 0. This is the quench. Okay, so one can verify that this FDT ratio gives you a result, because you can compute on this side, a result that is equal to tangent of the lambda q, and lambda q are the lambda Lagrange multipliers that were already computed for this problem. And that, well, I don't write the explicit expression, but they are known. And this occurs for wave vectors q and at frequencies omega q that are linked to the q via this relation here. Okay, so the same kind of game is played in this problem, and using an operator, an observable, which is kind of natural for this problem. It's not just, something that you cannot, or that people could not study experimentally. So there are other examples that we treated, the Ising chain and some other ones, but I just wanted to tell you that, to summarize, for all the integrable systems that can be mapped to free fermions, free bosons, oscillators, this procedure works, and we have verified it, and the FDT relations give you all the Lagrange multipliers of the GGE. The question remains as to whether, for the integral problems that people know how to solve in different ways, but that are not mappable in principle, or is not known at least how to map it to free objects,